All right. Good afternoon. Welcome back. It's day 2 of the homework. So pages 5 and 6 is all I have left. So we'll go through this. So first off, we're going to do solid, liquid, gas, or plasma. Remember, plasma is just most people call it superheated gas. It's only typically found in a couple places, lightning, and in the solar system like the sun, stars, things like that. Okay, so just keep that in mind when you're talking about plasma. We don't usually talk about plasma. We don't deal with plasma very much. You do see plasma actually when you do plasma cutting, if you were to use plasma torches and like welding. But other than that, we don't ever really deal with plasma. Most people will never deal with plasma in their life. Okay. So as we go through, we'll pick a couple of these. Most dense state. Well, most dense would be a solid. Okay. And so then we go down here to shape will not change. Oh, well, I think that's a solid also. Okay. Because you can't change the shape of a solid. And over here, completely fills container. So you have completely fills and then you have takes shape of container. So you have to be careful with those two. The take shape is a liquid and gas fills it. Okay, gas will fill it, liquids will take the shape of it. And then also least disorder. So disorder, remember you're thinking about how chaotic it is. Well, the least chaotic of all these is solids. All right, so I'll let you kind of work on the rest of these. Number three, let's jump three. In comparison to liquids and solids, gases generally. Okay, so let's think about it. So if I was to draw out solid, so there's a solid. Liquid would be a little bit more spread out, a little more random, somewhat. And gas would just be all over the place. All right, so let's see. They have more entropy. Okay, so does gas have more entropy? Does it have more randomness? Well, yes, so this is a possibility. Are more organized? Well, gas is definitely not more organized compared to solids and liquids. If we said it has more, can't have less, and are unable to change shapes. Well, solids and liquids can change shapes. So if it's unable to change shape, it has to be a gas. Oh, hold on. Oh, gases are generally unable to change shape. Yes, gases don't have shapes at all. It's not going to be that one. So it is A. They have more entropy. They have more entropy, which means they have more spread around, more randomness, more disorder in the system. Okay? All right, let's look at the back page, last page. So on this page, you have two different diagrams. And the first diagram is called a phase change diagram. Some people call it the butt diagram, okay? Because if you look, you have your crack right here, and then here's your cheeks, okay? And so the way it works is your solids are always here, your liquids are always here, and the way I kind of remember it, the solids and liquids are here, and then what's produced out of the bottom is gas. Okay? So that's kind of how I remember it. Probably not the right way, but there you go. It just asks you to do some things, so we'll just jump down to letter C. What is the pressure of the triple point? So triple point is where they all three meet. In part A, you're supposed to circle the triple point, so there it is. And then you just look. So temperature's down here, pressure's over here. So I'm just going to take and kind of draw out a line that's crooked as a jaybird. So I'll pull out my handy dandy sheet of notebook paper here. Okay, so it's about right there. And at that point, we'll call that 0. We'll go with 0.7 now. All right, and then of course, I always like to put my pressures with some numbers, with some letters, so it's ATMs, it's atmospheres. Okay, and so as you keep going down here, so let's look at F. Assume the substance is at 1.5 atmospheres and 0 degrees Celsius. Okay, so first let's figure that out. So atmospheres is on the vertical axis, the y-axis essentially. So 1.5 ATMs is right here. 0 degrees Celsius is right here. Okay, so that would put this as a solid at that point. The pressure is lowered to 0.25 atmospheres. What phase change occurs? So notice we're not changing the temperature, we're just changing the pressure. So now I'm going to draw the pressure out here to meet the temperature, and what happens? It's no longer a solid, but it's now a gas. Isn't that cool? Okay, so temperature stayed constant. The only thing that changed was pressure. Excuse me. And so originally it was a solid because it was in the solid area. And then once we lowered the pressure lowered it, and then it became a gas. Okay, so see how that works? Easy breezy, cool deal. All right, so down here, I'm just going to kind of sketch this line in. It's hard to see on the presentation. And this is called a phase change diagram. Okay. And so there you go. And then you have some letters. You have A, B, C, D, E. We're done. All right. And so once again, you're going to label these different points. So label it based on melting, boiling, condensing, freezing. Oh, excuse me. So melting would be right here. Okay, so melting would be when it starts off and it gets to a certain degrees Celsius, it's going to start melting. And as it increases, and if you hadn't figured out, this is water probably, because at 0 degrees it starts melting, and then at 100 degrees it starts boiling. And so remember, melting is a solid to a liquid, and boiling is you're right, liquid to a gas. Condense is reverse. So this is gas back to liquid. So this would be D, condensing. And then finally, freezing. Well, you got it. If I take liquid water, so this is a liquid, I'm going to freeze it into ice. So this would be right here also. So this is freezing. Okay. And so what happens is you apply heat. Notice you have energy down here. You're applying heat energy. So you apply heat energy, the temperature is increasing, and at certain areas it kind of stays put. It means that it takes a certain amount of energy before it makes it rise, the temperature rise again. Okay? And then you get here and notice that water boils for an exorbitant amount of time, or whatever this substance is, exorbitant amount of time before eventually it will start going up higher in the temperature when you get into some super hot, super absorptions of heat. Okay, that gets into some different levels and different things we won't talk about here. Okay, and so now if we start looking down here, well, F, what temperature is the freezing point? Well, we said freezing point is where it's going from here to here, right? Where it turns back into a solid. So the freezing point would be, looks like about 0. And then how much energy is added to evaporate the substance? Well, evaporate, what would evaporate be? Evaporate would be going from a liquid to a gas, right? So you think about the rain cycle. We evaporate the water. The water is down on the ground and it evaporates up. All right? And so you would look at, for example, at B is where it is melted. So now it's a liquid and it's going to go up. So this is going to be evaporate. So you would just calculate the amount of energy. So final, drawing a line down here. It looks about, use my cheat sheet notebook paper. Looks like it's just a little bit off 800, so we'll say, but there's not a lot of space. We'll say 850 minus, and then we'll look kind of right here, draw a line. Okay, well, we'll say, we can say 450, 500. And so you subtract it out, it'd be about 400 kilojoules. Okay. And remember, so it's final minus initial. As you go up, you'll be adding, so that's why this is positive kilojoules. Okay? And so that's how you'd figure it out. You just kind of draw lines, kind of gauge or guesstimate the location of those numbers, and then subtract them out. What we're looking at is that you're showing us you can do the skill set. That you can figure out this minus this is evaporation. Okay? The numbers are not as important because they're relative. Depends on what you look at. You could see it differently. You could say, oh, that's 429 to 846. Yeah. Yeah, you subtract them out, that gives me the numbers. So, all right. So that is phase change, or phase diagrams is what this is called. This is called the triple point diagram, also sometimes known as the butt diagram. So there's how to do that. So continue working on it. Good luck. And if you have any questions, check with your teacher. Remember, there is not a test over this material for this unit. We're not doing a separate test, but this stuff will be on your final exam for the semester. So you want to make sure that you understand it and learn it so that you can do it. All right. Good luck. Have fun.